Hello again, everyone. Sorry it took so long to get this episode out, but lots been going on lately. Anyways, I actually ended up building a new computer, so there's been a few changes with the project. As you can see, I'm running in Visual Studio 2017 now. I also, let's see, I'm using a newer Vulkan SDK, and I also had to redo all the dependencies for the project just to make sure it would run properly. So I'm not going to go through everything that I changed, but if anybody has any trouble, you can always ask questions in the comments and I can kind of go through how I got through everything and made it all work. So let's get right into what we're going to be doing here. In the last episode, if I remember right, I made an IndexBuffer. It made everything more efficient for drawing vertices to the screen. In this episode, what we're going to do, the IndexBuffer, if I remember right, it's in the vertex buffer, which probably isn't the best place to put it. Let's see here. Yes, okay, so all the code for the index buffer is inside the vertex buffer. And we're going to try and separate it out into its own class. And to do that, we're actually going to make we're going to take the PV buffer that we created and expand that a little bit more so that any of the buffers that are derived from the PV buffer class will have everything already built in there. Because we're also going to create another buffer in this episode. It's going to be it's a uniform buffer object, which is going to be storing all of the transformation matrices for the vertices that we're drawing, so that way we can actually render them properly to the screen. So before we actually get back into everything, let's just real quickly remind ourselves where we were at. So right now, if you run the project, you end up getting this nice rainbow rectangle, and it's not apparent that it's being drawn in any sort of 3D space. By the end of this episode, it will be, because you're actually going to be able to see it from an angle, and it'll be moving. It'll still be a 2D object, but you'll be able to tell that it is within a 3D space. And one other thing, you might be getting these errors. The Q family indices is not unique within the array. This is due to a bit of a typo that I made. It doesn't actually hurt the behavior of the project, though. It might be a little bit inefficient, but I'll still be able to continue without fixing this. I am going to fix it, but I'm going to do it at the end of the episode. So we'll get to that in a moment. Anyway, so let's get right into this. First off, we should probably move everything from the vertex buffer that references the index buffer into its own class. So let's go ahead and do that right now. So we have PV vertex buffer. I'm just going to create a new class. Alright, and this is going to be PV index buffer. Hopefully the new keyboard isn't too loud. Alright, and we're just going to copy over an awful lot from the vertex buffer. So, once again, we want to make sure this is including PV buffer, because it is derived from that. Oh, I don't need that. What am I doing? I just need this. There we go. Alright, and we want to make sure that index buffer is derived from buffer. You know what, actually we're just going to copy everything here. And then I can delete what's not necessary. This isn't necessarily the best way to go about it. There's a lot of potential for issues here, so I'm not recommending that you do this necessarily, but it'll work. Okay, so we'll do that. Make sure everything's referring to index buffer. Okay, we shouldn't actually need the vertices. And we shouldn't need these either. Okay, alright, now let's see what we can take out. Alright, so we also don't need any of this, because we don't need two getters. Okay, and we don't need two create and cleanups, we only need one. And I'll just leave them called that, create index buffer, and clean up index buffer, that should work. And let's see. I'm actually going to take, well, get indices size. We probably want to keep that, but get IndexBuffer. Honestly, any of the buffers that we make, we might need to get at some point, so it makes more sense to move this into PV_buffer. So let's go ahead and do that now. So we'll just head over to PV_buffer, and then right up here in public, we're just going to add a public getter. And we're just going to call it getBuffer, not getIndexBuffer. And we don't actually have a buffer to return, so we should store that in here as well. So let's hop back over to IndexBuffer. And we'll just get both of these, the buffer and the buffer memory. And drop those right down here under protected. I'm actually going to separate those, just so we have a section for functions and a section for variables. And these don't need to be called IndexBuffer and IndexBuffer memory. We're just going to call them buffer and buffer memory. And this will return buffer. Alright, so let's hop back over to the IndexBuffer now. Alright, so we've got the indices size, have all the create functions. I'm actually going to rearrange these. I'd rather have the getter down at the bottom there. That looks good. Okay, so that should be everything we need. Now we need to actually define all these functions. Just hop over to the CPP. Alright, didn't mean to close that. There we go. Alright, and let's expand all these out. Oh, actually, that's the constructor. So I'm just going to copy that up here and delete these two. Alright, expand these ones out. And we need to make sure they have the proper scope. There we go. Alright. And of course we need to make sure they're in the proper namespace, so we're going to go grab namespace PV engine and just wrap everything in that. Okay, so now we have everything here. Let's go ahead and start filling all this out. So for the constructor, we're just going to go ahead and call create IndexBuffer. That way we don't have to call it manually, just when we construct it, it'll already be ready to go. And we're going to pass in the logical device, the physical device, and the let's see, the surface, the transfer command pool, and the transfer queue. Okay, so this is all very similar to what we were doing before. We're just moving it all around. Alright, now we're going to create the IndexBuffer. Come to think of it, we probably don't need to be typing this all out. I can probably copy it all from vertexBuffer. Let's see here. So we'll just grab everything out of create IndexBuffer. Drop that here. Everything from cleanup. Drop that here as well. And then we'll just go through and we'll fix any of the errors with it. So we don't need either of these functions anymore in vertexBuffer. Still need cleanup, still need create. That all looks good. And then back over here, we don't need the indices anymore because those are now in the IndexBuffer. We don't need either of the IndexBuffer functions. We don't need either of the getters. And we don't need this getBuffer anymore because that's stored in the parent class. Just moving that one down there again just makes me feel better. Okay, and we shouldn't need either of these anymore because again those are stored in the parent class. And I'm guessing we'll get a few compile errors now. Yeah. here we go. So we don't need to call create IndexBuffer in the constructor. And down here in create buffer, we don't actually need to say vertex buffer anymore, we just say buffer and buffer memory, because those are all part of every buffer. And when we call copy buffer, we're going to want to do just buffer again. And let's see, same thing for cleanup. Okay. Alright, let's check back in with that index buffer. So, yeah, of course it's having some trouble too. It's just, this of course is going to be buffer, it's going to be buffer memory, buffer, buffer memory, and buffer. Okay. Now of course we still don't have anything actually utilizing index buffer. Since we moved it out of there, nothing ever constructs it. So we need to go back over to planetvulkan.h, and in here we need to create all the proper functions, or not the functions, rather, we need to create a handle to the index buffer. So up here we need to include, I'll just put it right here, just do include and pv index buffer. Okay. And we're going to come down here. Alright, there's our vertex buffer, and just underneath that we're going to add a pv index buffer, pointer, index buffer. Perfect. Alright, and now we're going to go over to the CPP and make sure everything gets deleted properly. Well, deleted and initialized and everything. Okay, so first we want to make sure that index buffer gets deleted properly. We're going to do that before we delete the vertex buffer. Okay, now we need to make sure that gets initialized. So right down here, right after we create our vertex buffer, we're going to create our index buffer. So we're just going to say index buffer equals new pv index buffer, and we need to pass in all the proper stuff, which I believe is the same as vertex buffer. That looks good to me. Alright, now we come down here to the cleanup, and originally we were calling vertex buffer cleanup index buffer, which doesn't make any sense anymore, so we changed that to index buffer. That does the trick there. And now we just need to clean up everything else in here. So, let's see. Probably having some little issues. Yeah, so right down here in create command buffers, we need to make some changes. So it looks like we just need to take this and change it to index buffer. And this should be get buffer. It doesn't make any sense for this to be called index buffer as well here, so I'm just going to shorten it so that there's not an inconsistency with the name there. We should change this to IndexBFR as well. And then down here in draw indexed, the index buffer is one that has indices, so there we go. And I believe that's everything. So let's see if we've gotten everything back into a state where it runs. Rebuild everything. Here, and that looks pretty good. So everything's still working exactly the way it was before. We've just kind of moved everything around. So now it's time to get into the good stuff. We're going to actually start creating our uniform buffer so that we can start performing transformations on our models. So we're going to make another class. Here we go. And this one's going to be PV uniform buffer. There we go. Alright, and just like before, this is going to be another buffer type, so we need to make sure it's very similar to all the other buffers we've made. So I'm just going to copy stuff from here. Make sure it has the proper namespace, make sure it's including PV buffer. We're going to make sure that it is derived from the buffer class. Alright. And I'm just going to copy all this. We may not end up needing any of it, but it might save me some time. Okay. Make these into the proper types there. Okay. So to start off with, we definitely don't need the indices right here. And for create IndexBuffer and clean up IndexBuffer, we're going to make a uniform buffer, of course. There we go. Alright, and the get size, that's going to be a little bit different. We're going to make this get uniform buffer size. And we'll come back to this in just a second, actually. But the type is going to be a VK device size. There we go. Yeah, but I don't have... We'll come back to what we need to return in just a moment. So up here at the top, we're going to add a new struct. So under public, we're going to make a struct, and this is going to be our uniform buffer object. And what this is, it's going to be passed into our graphics pipeline so that it knows how to transform things. And we're going to use GLM for this again. This is going to be GLM mat4 model, GLM mat4 view, and GLM mat4 proj. So this is the world or model view and projection transformation matrices that we're going to use. So now that we have this struct, I'm going to come down here to where we had get uniform buffer size, and that's just going to pass the size of the uniform buffer object. So we just do size of, and then uniform buffer object. So all this information here is information that we're going to want to pass to our graphics pipeline through the vertex shader. And the way we're going to do that, the reason we've created this uniform buffer is we're going to copy all that information into a VK buffer, and then we can pass that into our vertex shader using a uniform buffer object descriptor. So we're going to go ahead and set that up right now. I believe it's in tester game. Yeah. So we go into our shaders. We're going to open up the vertex shader. Oh. It looks like I didn't install Notepad++ on my new computer. Give me one moment. Alright, sorry for that delay. Let's try this now. There we go, much better. Okay. So we're going to go ahead and add that layout description for the uniform buffer object. So, right up here at the top, we're just going to say layout binding equals 0, uniform, and then uniform buffer object. And then we declare the structure of it, which is mat4 model, mat4 view, and mat4 proj. And down here we just put UBO and end it. There we go. And just so you're aware, the binding equals 0 right here, it's very similar to the location that we gave for the attributes. It allows us to reference this uniform buffer when we're writing our descriptor layout later on in our C++ code. It just helps it find it. So in theory, all this information will be passed in by our C++ code, and then we need to actually use that to transform our vertices. So down here, we're going to do that with the GL position. We're just going to type ubo proj times ubo view times ubo model, and all of that times the vec4 in position. And you may notice that we're doing this in reverse order. This actually matters. You do need to do it in order of projection, then view, then model, because matrix multiplication is not commutative. So if we do it in a different order, you end up with different values, and it doesn't do what you want it to do. So we do it in reverse order. Each one keeps modifying the next one, and when you're all done, these three end up creating the final transformation matrix that you use to transform this value here. Alright, so we have all that now. So we can close this now. And don't forget to compile everything. Ooh, actually, when I went ahead and changed everything, it looks like I forgot to change this. So the batch file that I wrote before, you'll notice that it's targeting the wrong version of Vulkan, and this folder is not going to exist because I have a different version of the Vulkan SDK, so I'm going to fix that up right now. Alright, so we're going to go ahead and open up the compile batch file, and let's navigate to where we have that Vulkan SDK. So we have C:\Vulkan SDK, and it looks like I'm using 68.0, so change that here. Alright, let's see if this runs better now. It should, but you never know. Okay, compile. And that does appear to have done the trick. Okay, if we run into any problems down the line, then I'll worry about it, but as of now, I think that did it. Alright, let's get back to the code now. So we have this half-finished PV uniform buffer here. We're going to go ahead and finish that off. So we want the create and cleanup functions to be defined. So we're going to drop those in here, and we're going to give them their scope. And a body. And we also want to make sure that we get the namespace again. Okay. Should be happy there. And let's get all the arguments from the constructor. Okay. Great, now it's not yelling at me. Alright, and we're just going to fill these out pretty much exactly the same way we filled out everything else. So I'm going to copy some stuff from IndexBuffer because I'm lazy. It's just the same thing as before. We're going to call create uniform buffer, and pass in the same arguments: logical, physical, surface, transfer command, pool, and transfer queue. And grab all this from create IndexBuffer. And the cleanup. There we go. Yeah, and the create uniform buffer is going to be slightly different, so we'll go ahead and tweak that a bit. We actually don't need an awful lot of this code, so vk device size buffer size, all we're going to do is we're going to use that function that we wrote before, the get uniform buffer size, and it's going to give us the size of the uniform buffer object. You could also just call size of uniform buffer object, but I figure why write a function if you don't use it? There we go. So that should do the trick there. And then we just call create buffer. So we don't need any of this, and we don't need any of this. Alright. And this one's going to be a little different, so we have logical, physical, surface, buffer size, and we want this to be vk buffer usage uniform buffer bit. We want visible bit, we want coherent bit, and then we just do buffer and buffer memory. We're not using a staging buffer for the uniform buffer, so this is all we need. Keep things nice and simple. Now there is one more thing we need. We actually want to create an update function for the uniform buffer. That's what's going to cause the positions to change as we go. So right down here under cleanup uniform buffer, I'm just going to make void update. And in this we're going to want a VK device pointer. That'll be our logical device. And we also are going to need a VK extent 2D, and it's going to be a reference to the swap chain extent. So ultimately what this update function is going to do when we're done with it is it's going to cause the rectangle that we've rendered to spin. So to do that, we're going to need to use some GLM functions to modify it. So up here at the top, we're going to call define. It's going to be GLM Force Radians, like that. And then we're also going to include, and this is GLM /GTC /matrix transform .hpp. So the purpose of these, GLM Force Radians is kind of self-explanatory. It just forces GLM transform functions to use radians as arguments. And then down here, this GLM GTC matrix transform, this exposes the GLM model view and projection transformations, things like rotate and look at, and you'll see those used in just a moment. And there is one other thing that we want. Down here we're going to include chrono, and this is going to allow us to do frame rate independent timing. Alright, so I'm going to show you how all those work right now. So we're going to go ahead and implement the update function. So over here, just drop down, get the scope. Alright, let's do this. So first off, we're going to calculate the time that the program started. So we're just do static auto start time. And this is going to equal std chrono high resolution clock now. So that'll give us the time in seconds since the rendering started. Next up, we want the current time, so we're going to type auto current time, and this is going to equal the exact same thing, just std chrono high resolution clock now. And the reason that these are different at all is because didn't mean to add that semicolon. The reason these are different at all is because this one is static. So when this first gets called, this will get declared, it'll get the time, and then this won't be constantly updated. It's because it's only declared once. So the start time and the current time will not always be equal. Alright, so next up, down here, we're going to do float time. That's going to equal std chrono duration. Oh, there we go. Duration float, and it's going to be, we need a period, so it's going to be std chrono seconds period, and we're going to calculate current time minus start time count. So that'll give us the amount of time that's passed. Alright, now we want to actually perform all the transformations. So we want to declare a uniform buffer object, UBO. Just give that a default construction there. And then we're going to set each one of its values. So we have UBO model, and this one's just going to be a general rotation around the z-axis relative to time. So we're going to do GLM rotate, and we're going to pass in GLM mat4. It's going to be 1 time times GLM radians. Do 90 GLM vec3, and this is going to be 0, 0, and 1. Alright. So in case you're wondering what all this information is, the rotation function takes in an existing transformation matrix, the angle to rotate it at, and the axis to rotate it around. So we're doing just an identity matrix. We're rotating it by 90 degrees, but we're converting it to radians. And we're also passing in time so that it modifies that by 90 degrees each second. And then the axis that we're using is going to be the z-axis. So it's rotating around the z-axis. So next up, we need to modify the view transformation matrix. So we're going to do UBO view, and this is going to equal GLM look at, and we're going to pass in GLM vec3, and this is going to be 2, 2, and 2. Then GLM vec3, and this will be zeros, and last, another vec3, and this one's going to be 0, 0, and 1. There we go. So by setting the view to this value, what we're passing in is the viewing position, the center position, and the axis that is up within this coordinate system. So up is our z-axis, the center is 0, and then we're viewing it from 2, 2, 2, which within that coordinate system would mean that we're looking down at the object from a 45-degree angle. Alright, now last step, we have the projection. So ubo.proj equals GLM perspective. And for this one, we're going to pass in GLM radians 45. Oh, that doesn't need a comma. What am I doing there? Alright, and then we do the swap chain extent width over float swap chain extent height, and then 0.1 f and 10 f. Alright. So in this case, the perspective for the projection is going to be from a 45-degree angle. This right here is just the ratio, so we can make sure that everything is sized properly if the window resizes, and these are just the near and far planes here. Now there's one last thing we need to do. GLM was actually designed for OpenGL, not for Vulkan, and they have slightly different coordinate systems. So because of that, we need to do ubo proj 1, 1, and we're going to multiply that by -1. And I'm just going to actually put a comment here. What we're doing here is we're flipping the y coordinate since GLM projection view is left-handed. There we go. So that'll make sure that everything matches up properly for Vulkan. So now that we have all of these transformations set up, we can copy all the data from the uniform buffer object into the uniform buffer that we've created. So we just need to do the same thing that we've done with any of our other buffers, although we don't have a staging buffer now, so it's a little bit easier. Just do void pointer data vk map memory, and we're going to pass in the logical device and the buffer memory, 0 for the offset, the size of UBO, zero for the flags, and then a reference to the data. Okay. Then we just do a mem copy. Data, reference to UBO, and size of UBO. And then we unmap memory, logical device, and buffer memory. And that is everything we need for our update function. So now everything should be set up for our uniform buffer. So it's time to set up everything regarding our uniform buffer in the actual Planet Vulkan code. So let's go ahead and do that. So we're going to want to create a pointer to the uniform buffer object. So we're just going to, right here, do pv uniform buffer. And of course it's not recognizing that because we haven't included it yet, so right up here we're going to add in pv uniform buffer. Alright. Now before we get into too much of this, if you remember in the vertex shader, we created this layout binding for a uniform buffer object. And when we do that, we actually have to create a layout binding descriptor so that we can link up to it properly. So we need to do that right now. So let's go ahead and go down to where we're right under create render pass. We're going to go ahead and create the Descriptor Set layout function. So we're just going to say void and create Descriptor Set layout. Okay, and let's go ahead. Go over to create render pass, and right underneath that, we're just going to drop this in. Alright, so this is going to set up everything so they can link to the vertex shader. Now before we actually start filling out any of the code for that, let's go up here to the top and make sure it gets called at the proper time. So we want to call that right after create render pass. That's why I placed it there. So we have create render pass, and we call create just kind of forgot what I was doing there. Create descriptor set layout. And actually, while we're here, why don't we make sure we don't do anything incorrect with that uniform buffer. So since we already declared our uniform buffer in the header file, let's make sure it gets deleted properly. We want to delete that before the index buffer, so delete uniform buffer. And we want to make sure that gets created too, so down here underneath index buffer, we're going to create the uniform buffer. It's going to be a new PV uniform buffer. We pass in all the usual stuff, so that should do the trick. And then also down here in the game loop, we want to continuously update the uniform buffer's transformation matrices. So right before we draw the frame, I'm just going to do update transformation matrices, and we're going to call uniform buffer update, and we're going to pass in the logical device and the swap chain extent. So that should all update properly now. Okay, now we can actually go and fill out the code for create descriptor set layouts. So let's jump back there. Okay, so first we want to declare a VK descriptor set layout binding, and we're going to call that just UBO layout binding. There we go. And then we're going to fill out all the details. So we have UBO layout binding dot binding, and remember we set that to 0 in the vertex shader. Then we have UBO layout binding descriptor type, and we're going to set that to VK descriptor type uniform buffer. We have UBO layout binding descriptor count, which is just going to be 1. And last up we have the stage flags. That's going to be VK shader stage vertex bit, since it's going into the vertex shader. We also need to set up a VK descriptor set create layout create info. There we go. We'll call that layout info. And so the layout info S type is going to be VK structure type descriptor set layout create info. There we go. I keep having trouble typing out descriptor. I'm not sure why that is. Alright, then we do layout info binding count, which is going to be 1, and layout info p bindings, which is going to be the reference to the UBO layout binding. There we go. And now we just need to create it. So it's going to be if VK create descriptor set layout, pass in the logical device, the layout info, null pointer for the allocation callbacks, and the descriptor set. Oh, actually, you know what? I don't think I ever made the descriptor set. So back here in the header file, yeah, I did create descriptor set layout, but I never actually made a handle to the descriptor set. Okay, well that's my mistake. We'll go ahead and add that in real quick. So what we want to do is right here, we'll put it right underneath render pass since that's roughly where it's called. We're going to make a VK descriptor set layout. There it is. Okay, and we'll call that descriptor set layout. Great. Okay, and then that's what we want to pass in right here, just a reference to the descriptor set layout. Okay, perfect. So we do all that, and if that does not equal VK success, then we failed, so we want to throw an error just like we've been doing. I'm just going to copy this whole thing right here. Nope, don't do that. There we go. Failed to create descriptor set layout. And then down here we do descriptor set layout created successfully. So that way we know whether this succeeds or fails. So perfect. This should now all work properly. So this function right here is creating a descriptor set layout, and it's explaining how they're bound and that sort of thing, but we still need to create an actual descriptor set. And similar to the way that command buffers are allocated from a command pool, descriptor sets need to be allocated from a descriptor pool. So we need to set that up as well. So back here in the header file, we're going to go ahead and create a descriptor pool. I'm going to put it we have the graphics command pool and the transfer command pool. So why don't we put it right around there? Put it right underneath, I guess. So we're going to put VK descriptor pool. And that's going to be descriptor pool. There we go. And we should also go ahead and declare the descriptor set. So I'll just put that down here at the bottom. Just do VK descriptor set. And that's descriptor set. Okay. And now we need functions for both of those, one to create the pool and one to create the set itself. So we go back up here. Descriptor set layout right here. Okay, so we're going to do create descriptor set layout, then create descriptor pool, and then create descriptor set. Alright, let's go and actually make those do something. So right underneath create descriptor set layout, we're going to add in those two new functions. Give them scope, give them body. Alright, so let's make sure that these get called properly. You just go back to the top. And right after we create our uniform buffer, but before the command buffers, we're going to go ahead and call create descriptor pool, and then create descriptor set. Remember, we got to do the pool first because that's where it's being allocated from. Okay, and let's fill these out for real now. Oh, actually, there's one more thing. Totally forgot, and this is bad. Got to make sure we clean it up properly as well. So, let's see, where did we do clean up IndexBuffer, swap chain, so right in between these two we should have it. So we want to call VK destroy descriptor pool, and that takes in the logical device, the descriptor pool, and we'll do a null pointer for the allocator, allocation callbacks. Then we need to clean up the descriptor set layout, so VK destroy descriptor set layout. Logical device. And descriptor set layout. Null pointer. It's pretty straightforward. Kind of the same format for each one. And did we ever clean up the uniform buffer? Doesn't look like we did that either, so we should call uniform buffer. Clean up uniform buffer. And that expects a reference to the logical device. Okay, so hopefully everything is being cleaned up properly now. And for real this time, let's go ahead and fill out these functions. So we'll start with the pool. I'm going to do this one backwards again. I don't know why I decided to do this one in forwards order. I feel like it makes more sense when you go backwards. So we're going to go ahead and call vk create descriptor pool. And that expects a logical device and a pool create info. And then it would be null pointer, and the descriptor pool right here is what's getting modified. So make sure we have the proper information being passed here. Okay, so what was it we needed again? The descriptor pool create info. So we do a vk descriptor pool create info. Call that pool info. And then this here should be pool info. And we need to fill out all the information for the pool info. So it's going to be pool info s type, which is going to equal vk structure type descriptor pool create info. Then we have the size count, which is going to be 1. Pool info p pool sizes. And this requires a reference to a vk descriptor pool size, so we'll do that one in a second. Right now I'm just going to say reference to pool size, and we'll fill that out in a moment. And then pool info max sets, which is 1. Alright, so we need to fill out that pool size real quick. So vk descriptor pool size. My typing is a little off today. That's okay. So pool size, s type, not type, s type. Oh no, it is type. I'm getting confused. And this is going to be vk descriptor type uniform buffer. And the pool size descriptor count equals 1. So that should be all the proper information to create a new descriptor pool. And now, assuming that that gets created successfully, we should be able to create our descriptor set. So let's do this one. Yeah, we'll do this one in reverse order as well. So this one, it's not actually a create call, it's if vk allocate, oh, I'm totally typing that wrong, vk allocate descriptor sets, and it wants a logical device, reference to the allocation info, which we haven't actually made yet. We'll do that in a second. I'm going to call it alloc info, and the descriptor set that we are creating. copy all my error checking from up here, just drop it down there. Alright, so now we need that allocation info. So we just do vk descriptor set allocate info. And we need to fill out all the information for it, so allocinfo dot s-type, and that's going to equal vk, jumped a little further than I meant to there, vk structure type descriptor set allocate info. Okay. Allocinfo wants a descriptor pool, which is going to be the descriptor pool that we just created. It wants a descriptor set count. We only need the one. And it needs a pset layouts, which we haven't actually created, but this is a this is going to be an array of vk descriptor set layouts. Oh. There we go. VK descriptor set layouts, and we're just going to pass in the descriptor set layout that we made when we initialize that array. And then we pass in layouts right here. So that should create everything successfully. And then we need to make sure everything gets updated. So we're going to call vk update descriptor sets. This expects logical device. For the write count, we're just passing in 1. We need a vk write descriptor set, which we haven't done yet, but we'll do it in a moment. I'm just going to call that descriptor write, if I could spell. Then a 0 for the copy count, and null pointer for descriptor copies. So to make sure we have all the info for this, there's lots of backtracking here. We're going to need a vk write descriptor set. I'm really having some spelling trouble today. I apologize. So, descriptor write s-type. This is going to be, as usual, vk structure type write descriptor set. We need a dest set, which is descriptor set. Dest binding, which is 0. That's the binding we gave it. Dest array element, which is 0 because it's the first one in the array. It's the only one in the array. Descriptor type, which is vk descriptor type uniform buffer, as we put in before. descriptor right, descriptor count, 1. It's a lot of info, but it's important. And p buffer info, which is a reference to buffer info, which we have not filled out yet, but I'm going to do that just above it. This is a VK descriptor. This is all very repetitive. Buffer info. There we go. Great. And for the buffer info, we just want to have buffer, which is going to be the uniform buffer that we created before. This is where it all ends up linking in. And we're going to say get buffer. And then the offset is, of course, 0. And one more thing, we have the range, which is going to equal uniform buffer. And we're going to call get uniform buffer size. Alright, and I believe that is everything we need. Alright, now there's just a few tiny things left to do. If we go back to create graphics pipeline, so in here, where is it? There should be a place where we do the pipeline layout info. That's probably... Here we go. Ah, here it is. Okay, so pipeline layout info, and before we only had the S type, but that's handling any of the descriptor set layouts. So what we want to do is we want to do pipeline layout info, and we're going to add in a couple things that we didn't bother to define previously. So we're going to have set layout count, which by default is 0. We're going to set that to 1. And then pipeline layout info, pset layouts, and we're going to make sure that it references the descriptor set layout. There we go. And there's one last thing that we need to do. It should be up just a little bit from here. So for the rasterizer, we passed in VK front face clockwise. And the problem is in our, I think it was back here. Yeah, if you remember, we flipped the y coordinate for the projection view. Because of that, over here, if we pass in front face clockwise to the rasterizer, because everything's been flipped, it's going to end up culling all of the images, so we won't actually be able to see anything. So instead, we want to change this to counterclockwise. So just there we go. And hopefully everything should run properly now. Let's find out. So let's give this a run, and let's see what we get. Hopefully there's no compile errors. Does not appear to be working. Let's find out why. Okay, so it turns out I missed one more line that was important. If we jump down here to bind IndexBuffer, gotta actually spell it right again. Okay, so down here this is in create command buffers. So we call bind vertex buffer, we call bind index buffer, but we need to actually bind the descriptor sets. So right underneath that, we want to call vk cmd, then bind descriptor sets. And we want to pass in the command buffers, vk bind, vk pipeline, bind point graphics. There it is. That didn't work. There we go. Pipeline layout, 0 for first set, 1 for descriptor set count, and a reference to Descriptor Set. There we go. Offset count is going to be 0, and dynamic offsets is going to be null pointer. Okay. So let's see if this works now. There we go. So now, like it was before, you have a 2D rainbow rectangle, but now because we're at an angle and because it's moving, you can tell that we could potentially move the camera around here and actually see it from different angles and understand that this is a 3D object. So, I mean, that's really all we had to do. Everything seems to be working nicely. The last thing, though, is I did promise I would fix this annoying little error here, so let's go ahead and take care of that now. So, to put it very plainly, this error that we're seeing here, it's actually very descriptive. What it's saying is that the Q families, I mean, like it says, they're not unique. So what that means is if we go back to PV Q family right here, at the beginning when we call find Q families, you'll notice that I'm trying to find dedicated graphics and transfer families. And then at the very end, if there's a graphics family and it wasn't able to find a dedicated transfer family, it sets them equal. Because the graphics family can also be the transfer family, that's not a problem. But what the code is supposed to be doing is supposed to be determining whether it can find a dedicated transfer family that won't be used by the graphics family. On my case, that's not happening. And in a lot of cases that won't happen. So what we need to do is we need to determine whether or not these two are equal when we start calling findQ families. So over here in, where is it? PV buffer. When we call create buffer, I have it calling findQ families, and then it sets up an array with the graphics family and the transfer family. And it tells, in the buffer info, it says that there's 2 Q families. But when it starts actually running through the code, it's going to realize that both of these are exactly the same. So what we actually want to do is, even though we have 2 of them, right here we just want to do a check to see if they're the same. So right here, let's see what the best way to go about this would be. Let's probably do this. We'll say if indices graphics family equals indices transfer family, else. So currently this else here is assuming that the 2 of them are different. But since we know they're going to be the same, we want to go up here and make all the same code, except this is going to be 1, and this one we're just going to pass in the graphics family, because we know that they're equal. There might be a more efficient way to write this, but this should do the trick. And you know what, actually we can take this and just move it underneath, since it's going to be the same for both of them. The count is going to change, the array contents are going to change, but... oh, actually, you know what, that's not going to work because we're declaring the array inside. I'm just going to put it back. I don't love the duplicate code, but it shouldn't hurt anything. So let's try running that now and see if we still get the error. Alright, so if pcreateinfo sharing mode is vk sharing concurrent. Alright, so it looks like this sharing mode right here is going to be affected by the Q families as well. So let's go ahead and take that. These are equal. Then we can't have it be sharing mode concurrent. So now we get concurrent sharing mode if we have a dedicated transfer and graphics family. We get exclusive sharing mode if we only have the graphics family and that's being used as the transfer family. So let's go ahead and see if that actually fixed the problem. And yeah, we are no longer getting any errors. So like I said, the errors before weren't actually hurting anything, but this is at least a more efficient way to be doing things. So there you have it. I mean, we've got our nice 3D rotating rectangle now. So that's all for this episode. In the next episode, we're going to start setting up loading in images for textures. So thanks for watching.